Here we are with part 2 of the color notes. When paints or dyes are mixed, the mix absorbs all the frequencies each paint or dye absorbs. Red and green paint do not combine to form yellow as red and green light do. The mixing of paints and dyes is an entirely different process from the mixing of colored light. Paints and dyes contain particles of pigments that produce colors by absorbing light of certain frequencies and reflecting others. Yellow paint reflects mostly yellow light, but also red, orange, and green. It absorbs blue and violet light. When blue and yellow paints are mixed, then between them they absorb all the colors except green. This process is called color mixing by subtraction. Mixing colored light is called color mixing by addition. When you cast lights on a stage, you use the rules of color addition, but when you mix paint, you use the rules of color subtraction. The three colors most useful in color mixing by subtraction are magenta, yellow, and cyan. Magenta, yellow, and cyan are the subtractive primary colors used in painting illustrations in full color, like what your printer does. Here is a table showing you everything, the pigments, what they absorb, and what they reflect. Color printing is done on a press that prints each page with 4 differently colored inks, magenta, yellow, cyan, and black. Each color of ink comes from a different plate, which transfers the ink to the paper. The ink deposits are regulated on different parts of the plate by tiny dots. The overlapping dots of 3 colors plus black gives the appearance of many colors. Only 4 colors of ink are used to print colors illustrated in photographs: magenta, cyan, yellow, and black. Which visible frequencies are absorbed by a mixture of paints or dyes? The sky is blue because its components particles scatter high-frequency light. Oh, I didn't press the button. This seems like a question we've talked about sometime in class. Scattering is a process in which sound or light is absorbed and emitted in all directions. Light is scattered by molecules in larger specks of matter that are far apart from one another in the atmosphere. A beam of light falls on an atom and causes the electrons in the atom to move temporarily in larger orbits. The more vigorously oscillating electrons may emit light in various directions. Atoms and molecules re-emit light waves. Very tiny particles do the same. The nitrogen and oxygen molecules and the tiny particles that make up the atmosphere are like tiny bells that ring with high frequencies when energized by sunlight. Like the sounds from the bell, the light is sent in all directions. Most ultraviolet light is absorbed by a layer of ozone gas in the upper atmosphere. The rest is scattered by atmospheric particles and molecules. Of the visible frequencies, violet light is scattered the most, followed by blue, green, yellow, orange, and red in that order. Violet light is scattered more than blue light, but our eyes are not very sensitive to violet light. Our eyes are more sensitive to blue light, so we see the sky look blue. Ta-da! See, violet light was scattered first, but our eyes can't see violet. Then blue is scattered, so that's why we see the sky being blue. The blue of the sky varies under different conditions. When there are a lot of particles larger than oxygen and nitrogen molecules, the lower frequencies of light are scattered more. This makes the sky look less blue, and it takes on a whitish appearance. After a heavy rainstorm, when the particles have been washed away, the sky becomes a deeper blue. The higher that one goes in the atmosphere, the fewer molecules there are, the sky appears a darker blue. When there are no molecules, as on the moon, for example, the sky is then black. Water droplets in a variety of sizes, some of them microscopic, can make up clouds. The different sized droplets result in a variety of frequencies for scattered light. Low frequencies from larger droplets and high frequencies from other droplets of water molecules. The overall result is a white cloud because it's scattering all the light. So why is the sky blue? By the time a beam of light gets to the ground at sunset, all of the high-frequency light has already been scattered. Only the lower frequencies remain, resulting in a red sunset. The lower frequencies of light are scattered the least by nitrogen and oxygen molecules. Red, orange, and yellow light are transmitted through the atmosphere more readily than violet and blue. Red light, which is scattered the least, passes through more atmosphere without interacting with the light of any other color. At dawn and at sunset, sunlight reaches us through a longer path through the atmosphere than at noon. At noon, sunlight travels through the least amount of atmosphere, so a relatively small amount of light is scattered. As the sun is lower in the sky, the path through the atmosphere is longer, and more blue is scattered from the light. Less and less blue remains in the sunlight that reaches Earth. The sun appears progressively redder, going from yellow to orange and then finally to red. By the time a beam of light gets to the ground at sunset, only the lower frequencies survive. If you look at this thing, it's saying at noon, this is how far the light has to travel, and then as the day goes on, the sunlight has to travel a longer and longer distance, so the lower frequencies like red can come out. The colors of the sun and sky are consistent with our rules for color mixing. When blue is subtracted, the complementary color that is left is yellow. The subtraction of violet leaves orange. When green is subtracted, magenta is left. The relative amounts of scattering depend on atmospheric conditions, changing from day to day for a variety of sunsets. As you see, as the sun is setting, it has a lot more atmosphere to go through. That's why you're seeing the reddish tint to the sky. The sunset sky is red because of the absence of high-frequency light. You see the scattered blue when the background is dark, but when the background is bright because the scattered blue light is faint. When you look for Earth's surface at the atmosphere against the darkness of space, the atmosphere is sky blue. When astronauts look down through the same atmosphere to the bright surface of the Earth, they do not see the same blueness. If molecules in the sky scattered low-frequency light more than high-frequency light, how would the colors of the sky in sunset appear? If low frequencies were scattered more, red light would be scattered out of the sunlight on its long path through the atmosphere at sunset, and the sunlight to reach your eye would be predominantly blue and violet. So it would be opposite of what we see now. So we have distant dark mountains are bluish in color. What is the source of this bluish? Here's your hint. What is between you and the mountains you see? If you look at distant dark mountains, very little light from them reaches you, and the blueness of the atmosphere between you and the mountains predominates. The blueness is of the low altitude sky between you and the mountains. And there you go, why are sunsets red? I think that was a question on your color book. Water is greenish blue because water molecules absorb red. We often see a beautiful deep blue when we look at the surface of a lake or the ocean. That is not the color of the water, it is the reflected color of the sky. The color of the water itself, as you can see by looking at a piece of white material underwater, is a pale greenish blue. Ocean water is cyan because it absorbs red. The froth of the waves is white because as droplets of many sizes scatter in many colors. Water is transparent to nearly all the visible frequencies of light. Water molecules absorb infrared waves because they resonate to the frequencies of infrared. The energy of the infrared waves is transformed into kinetic energy of the water molecules. Infrared is a strong component of the sunlight that warms water. Water molecules resonate somewhat to the visible red frequencies. This causes a gradual absorption of red light by water. A 15-meter layer of water reduces red light to a quarter of its initial brightness. There is very little red light in the sunlight that penetrates below 30 meters of water. The complementary color of red is cyan, a greenish-blue color. In seawater, everything at these depths looks greenish and blue. The sky is blue because blue from sunlight is re-emitted in all directions by molecules in the atmosphere. Water is greenish-blue because water molecules absorb red. The colors of things depend on what colors are reflected by molecules and also by what colors are absorbed by other molecules. Distant snow-covered mountains reflect a lot of light and are bright, but sometimes they look yellowish depending on how far away they are. Why are they yellow? Hint, what happens to your reflected white light as it travels from mountain to you? Distant snow-covered mountains often appear a pale yellow because the blue and the white light from the snowy mountains is scattered on its way to you. The complementary color left is yellow. Why is water greenish-blue? That's what we just covered. After an excited atom emits light, it returns to its normal state. Every element has its own characteristic color when it emits light. The color is a blend of various frequencies of light. Light of each frequency is emitted when the electrons change energy states. Electrons have well-defined energy levels, low energy levels near the atomic nucleus, and higher energy farther from the nucleus. When an atom absorbs external energy, one or more of these electrons is boosted to the higher energy level. Should have talked about these kind of things in chemistry when you have all your different orbitals, all the different energy levels of electrons, and you can move the electrons out from the center. The energized atom is in an excited state. And an excited state is a state with greater energy than the atom's lowest energy state. The excited state is only momentary, for the electron is quickly drawn back to its original or lower level. When this electron transition occurs, the atom emits a pulse of light, or a photon. Light is emitted by excited atoms. If you look at this coming in, it's a picture of an atom getting excited and expelling a photon. The different electron orbitals in an atom are like steps in an energy level. As you see, as it moves from, oops, I didn't hit my button. If it goes from this level to this level, it's becoming more and more excited. Until all of a sudden, bam, you get the photon. And you get the photon emission, and then the other goes back. It goes back down to the center. All right, relating frequency and energy. The frequency of the emitted photon, or its color, is directly proportional to the energy transmission of the electron. So frequency and energy are very close. A photon carries an amount of energy that corresponds to its frequency. Red light from the neon gas, for example, carries an emitted amount of energy. A photon of twice the frequency has twice as much energy and is found in the ultraviolet part of the spectrum. When many atoms in a material are excited, many photons with many different frequencies are emitted. They correspond to electron transitions between different levels. Measuring the frequencies of light in a spectrum is also measuring the relative energy levels in the atom emitting that light. The frequencies or colors of light emitted by the elements are the fingerprints of these elements. The light from glowing elements can be analyzed with an instrument called a spectroscope. The spectroscope displays the spectra of the light from hot gases and other light sources. Spectra is the plural for spectrum. The spectra of light sources are viewed through a magnifying eyepiece. A fairly pure spectrum is produced by passing white light through a thin slit, two lenses, and a prism. As you see, it goes through the prism, the slit, or the two lenses, and the slit, and then through the prism, and it breaks up all the light. A spectroscope separates light into its constituent frequencies. Light illuminates the thin slit at the left, and then it focuses by the lens on either of a diffraction gradient, as shown, or a prism or a rotating table in the middle. When light from a glowing element is analyzed through a spectroscope, the colors are the composite of a variety of different frequencies of light. The spectrum of an element appears not as a continuous band of colors, but as a series of lines. Each line corresponds to a distinct frequency or light in a line spectrum. Here are some examples. An incandescent light bulb has a continuous spectrum. Three elements, hydrogen, sodium, and mercury, have different line spectra. So this first one is the incandescent light bulb, and you have all the colors here. Where hydrogen only has these colors, sodium has the one, and mercury has these. So whenever you run it through a spectroscope, this is what you're going to see. Much of the information that physicists have about atomic structures from the study of atomic spectra. The atomic composition of common materials, the sun, the distant galaxies, is revealed in the spectra of these sources. The element helium, the second most common element in the universe, was discovered through its fingerprint in sunlight. What happens to an excited atom after it emits light? Produces a photon. That's the end of the notes for color.